Thank you very much for the invitation. So yes, before the title, something more important. So I want to show this excerpt from Fleur's paper. Partly this is some kind of penance on my part because I forgot to put this reference in the paper with Andrew Blumberg when we proved this result on Hamiltonian Fleur theory. But so what I want to say is that all this work that we're doing was in some sense envisioned by Fleur, in 1989, probably a little bit earlier. So this is the paper, Witten's complex infinite dimensional Morse theory, where he basically discusses this modern approach to the Morse complex, which goes back to Witten, where you have a generator for every critical point and a differential for the term of the differential for every trajectory, for every flow line. And he says, well, we should be able, the fact that the trajectory spaces are framed tells us that we should be able to do this for generalized cohomology theories. And then he explains a little bit. It's not clear he knew how to do it, but he had an idea that it should be possible. And the very end, he says, this program is only of limited use for finite dimensional Morse theory, roughly speaking, because there's only so much that you could hope to extract from Morse theory that can't already be done using classical methods, but it might have applications to infinite dimensional cases. So today's talk is not really about Morse theory. We will end up only using, closed moduli spaces, and there won't be any differential and so on and so forth. Nonetheless, it's in the spirit of the applications that I hope Fleur had in mind. So the talk is about joint work with Mark McLean and Ivan Smith. It's about classical problem that was studied in the 90s using Gromov, using moduli spaces that appear in Gromov-Witten theory. I'll come back to that in a second. But I want to start with, I just want to start with a conjecture, because there's a conjecture that arises because of this work. I don't think I would have guessed it before. So let me tell you the conjecture. So the context is that we have a closed symplectic manifold. It's called X. Associated to this symplectic manifold is a group, which I think almost everybody in this audience knows more than I, the Hamiltonian diffeomorphism group. And I want to study this group. And, I don't want to study it in the, geometric way, which is, follows from Hofer's work. I'm not going to talk about the Hofer metric. I'm not going to talk about, deep questions about the geometry of this group. I want to talk about simple, basic questions, much more basic questions about its topology. And one way you could study this topology is look at the inclusion of the Hamiltonian diffeomorphism group inside the diffeomorphism group. And the point is that the diffeomorphism group is extremely well studied. There's no higher dimensional manifold for which we can tell you, for example, what the topology is explicitly. There's no higher dimensional manifold for which we can compute the all the homotopy groups and all the homology groups, but we can usually do this in a range. So if the manifold is sufficiently, the dimension of the manifold is sufficiently high, then you can compute, for example, the homotopy groups of the diffeomorphisms of a ball up to some range that's about linear in the dimension. So, and I said ball to indicate that even the diffeomorphism of the ball is very interesting group. Okay, but I'm not going to do that. That's very delicate work. I'm not going to try to tie to that delicate work. I'm going to keep going. So then you could instead try to study the homeomorphism groups, and that's again something that's well studied. Or you could go to some object which already becomes a little bit looser. So this alt X means self-homotopy equivalences. So here you kind of, you look at maps that just have inverses up to homotopy, okay? And as I write, we throw away more and more information, okay? But even the last step, when we look at self-homotopy equivalences, such maps still preserve, for example, the ring structure on cohomology, okay? But in this talk, we will go even more. We'll forget even more information, and following the lead of the stable homotopy theorist, to try to compute something more, to obtain something more computable, for which we can almost write explicit answers, we're going to instead look at stable autoequivalences. Okay? So stable autoequivalences in homotopy theory, this is something you can do for any space X. What you can do is you can if you imagine that your space is constructed by some kind of handle attachment, this familiar picture when we do when we study, for example, a Weinstein manifold. And now what I want to do is I'm going to uniformly raise the dimension of all the handles. Okay, that's what suspension does. Okay, so formally what you do is you take the product with the sphere, okay? And then that has twice as many handles as we had before. The original ones, which is basically x cross a point, and the new ones, which is x cross the actual sphere. So we kill the ones called x cross a point. We just collapse them, and that's the suspension. So instead of looking at x itself, I'm going to look at the, again, the result of suspending x. This is what this procedure is called, n times, in fact, an arbitrary number of times. And in each, so this stable automorphism group, stable self-homotopy equivalences, it's basically the, I'm going to for now just use this, the limit of the automorphism groups of the suspension of x. Well, that's all, suspension of x, okay? So you over n. You make this n larger and larger. And when you do this, a lot of structure disappears. And in some sense, we're in a situation where we can almost say that we're dealing with a problem of linear algebra, but not exactly linear algebra, some kind of higher linear algebra. And you know, the point that I want to make is that this ring structure in cohomology, for example, disappears. And the only thing that's left is the additive structure on cohomology. So for example, there is there is a natural map from the homology of this space of stable automorphisms to the endomorphisms of the homology. And what you do is you say, oh, well, you know, every automorphism, it takes a cell to some other cell, okay? And every family of automorphisms, if I take a cell, it sweeps out some high dimensional cycle in the space. And then you can take that high dimensional cycle and see which cells are covered. So this is the statement that I want to make the conjecture about. I want to make a conjecture about the map from Ham X to stable automorphisms of X. Okay, and at some point as we were done writing the paper, I wanted to say that that this map is essentially trivial if you study certain generalized homology theories, but it turns out to not be true. It's not quite true. There's counterexample for X is a two-sphere, but the conjecture is about what happens when you pass to the loop space. So I'm going to maybe use a different color to indicate what's going on here. Pass to the loops. Yes?
What do you say about S out to end, to the endomorphism of
this map here?
Yes.
So that map, so what is an element of the homology of S out? An element of the homology of S out is a cycle.
Mohammed, I understood how it's constructed. I just wondered, do you claim that it's injective, surjective, bijective, something?
I will make a claim in 1 second that is completely precise, but right now I have no claim yet about that. Okay, I claim that map, I'm going to make a claim that it vanishes after passing to the loop space, but only on integral homology. Yes, I claim that it vanishes in integral homology, but not this map. Some map that's associated to loops. Is that okay? So this, I make no claim. Okay. So I want one more step, which is that I want to pass to the loop space of the Hamiltonian diffeomorphism group, which means I'm going to look at families of circles, S1s, mapping into the Hamiltonian diffeomorphism group. And similarly, that gives me a loop of stable automorphisms. Okay. And this you can do not just with one loop, you can do it in a family. This is a map of spaces. So now comes the main claim. So this is the main conjecture, which is that if we look at a complex-oriented cohomology theory, and if you don't know what that is, I will say something in a minute, but you can think integral homology. That's perfectly fine. Then this map vanishes with respect to this cohomology theory, and in fact, it vanishes at the chain level, whatever it means to vanish at the chain level. Okay, and in particular, not only so once this map vanishes, you conclude that this map, vanishes in homology, but also that the map from loop Ham, the map from loop mx, and here I'm going to put from the homology of loop mx to the, so it's kind of annoying to write it as endomorphism. Let me write it as a hom star plus 1 from the homology of x to the homology of x. This map is null. So that's the claim. If you want some kind of concrete claim about integral homology, the claim about integral homology is that if we take the homology of the base loop space of the Hamiltonian diffeomorphism group, we get some sweep out map of one higher degree that raises degree by 1 from the homology of x to itself, and that map is trivial. Okay, I'm worried that nobody can hear me. No, it looks like everything's okay. Okay, good.
Oh, I can hear you.
Okay, so that's the conjecture. So what I want to explain is the input of this conjecture, the fact that there's a statement about complex-oriented cohomology theory. I want to say a few words about what that means. Then I will explain what we can prove, which is basically right now we can prove the pi zero part of it. And then I will say a few words about how you can interpret this, and then I will start discussing the proof. Okay. Okay. So what are these complex-oriented cohomology theories? So this is some part of stable homotopy theory, but really it's the definition usually is there is some object which I'm going to call E. And it's a functor. The homology is like a functor from spaces to abelian groups. So you give me a space, I give you an abelian group. You give me a map of spaces, I give you a group homomorphism. And it should have some properties. But I'm not going to go too much into details. But the key property is that if you have a homotopy equivalence, that always induces an isomorphism. And in some sense, this is the most important part. You have Meyer-Vietoris. Okay, if you take a space, you break up into pieces. You can compute the homology by understanding the homologies of the pieces and the maps between them. And then there's one last bit, which is this statement that if you already introduce this suspension, that the homology behaves well under suspension. You just raise degrees. So ordinary homology satisfies all these axioms. And the point is that there are other ones around. And in some sense, this is kind of a strange thing to say, but in some sense, homology is not a very geometric one. And there is kind of much more geometric generalized cohomology theories, which go under the name of cobordism theories. Okay, so we'll be using one of them. What I want to say, but somehow in the statement there was this condition of being complex oriented, and what does that mean? Well, once you have homology, it turns out with just some small extra assumptions, you can obtain a cohomology group. And also something which like a compactly supported theory. I just want to introduce these because I need them for my kind of ad hoc definition of what it means to be complex oriented. Okay? So when I teach algebraic topology, the main result that I want to make sure the students understand is the statement of Poincaré duality. And it turns out that you have Poincaré duality is not just a statement that you can make in ordinary homology, you can make it in other cohomology theories. And of course, we all know that Poincaré duality is something that it doesn't make sense if you're working with integral homology, it doesn't make sense for every manifold. If I give you RP2, there's no Poincaré duality for RP2 with integral homology. And so a complex-oriented cohomology theory is one for which we have a Poincaré duality isomorphism for almost complex manifolds. Okay, so I stated it in the open case, which is why I had to introduce this compactly supported cohomology. So compactly supported cohomology is isomorphic to homology, okay, with a shift. And I stated it so that basically the statement could be as short as possible. If I state this only for compact manifolds, then I have additional pieces of data. And this just ensures that we just have all the data that we want. So now you could say, now what are examples of cohomology theories which are complex oriented? And as I said, the first one you could have is ordinary homology, and also FP homology if you want, and of course Q and whatever any discrete ring, any ordinary homology theory with whatever coefficients is going to have satisfy this property. But in some sense, the main point of this talk is that we should study the Fleur's excerpt that I said is that we should study other ones. And the other one that the focus is going to be on is complex cobordism. Okay, And that will be the conclusion. It turns out it will also use some other tools which are much more exotic. And these are these Morava K-theories. And I will say very little about them. But all I'm trying to say is that there are many, many examples. But the way that we should think about it is that this is the most important one, complex cobordism. And this can be formalized. It can be formalized because, as I write there, so it's known that complex cobordism is universal, is initial among these things, which means if you take any other cohomology theory, there'll be a natural map. I'm doing homology here. There'll be a natural map from the homology of M with coefficients in complex cobordism to the homology of M with coefficients in E. And so if you kind of establish something strongly, something sufficiently robust about complex cobordism, then you can conclude it for all these other theories. Okay, so that's what I mean by complex-oriented cohomology theories. It means basically you can ignore the definition and think about complex cobordism. But now, what is complex cobordism? Complex cobordism is just you look at manifolds. So the target. Oh, I shouldn't have used M here. I should have used X. There's a reason. Should have used X there too. Okay. So the complex cobordism of X. Omega U X. So this is, which is, again, sorry, there's two notations that clash with each other, and I switch back and forth. So this is basically, you look at all maps M to X, where the domain is compact, let me say closed, almost complex manifold. And you study them up to cobordism. And the reason this is going to be important for us is twofold. One is that the symplectic manifolds have almost complex structures. Hence, they have stable almost complex structures. Hence, they satisfy Poincaré duality for these theories. But also, in some sense, more importantly, the moduli spaces of pseudo-holomorphic curves have this natural structure. And we'll come back to that in a moment. Okay. So now, unfortunately, we kind of know by now in Floer theory that studying results just at the level of homology, okay, is usually, usually loses a lot of information. And instead, we often want to work at the chain level. So I said at the beginning, I said, well, something induces an isomorphism on homology, but actually the result, something is null at the chain level. And this will show up later. What does it mean, however, to work at the chain level when you're studying one of these generalized cohomology theories? Well, it turns out that working at the chain level does not mean that you have a chain complex and a differential and blah, blah, blah. Instead, what it means is you're working with topological spaces. Okay? If you have a generalized cohomology theory, again, we go back to this formal context we call it E. What you can prove just formally, it's not very useful to prove it formally, but nonetheless, it's useful to know about it, is that there's a collection of topological spaces, one for each natural number. Now, remember, when I introduced homology theories, one of the things I talked about is this notion of suspending, X goes to suspension, which is basically raising the dimension of the cell. And this procedure is very similar. Sometimes it's in some sense dual, but that's okay. And now I said that there is a cohomology theory, which is, again, some group, which is contravariantly assigned to maps of spaces. And it can be expressed in terms of these spaces as you look at the space of maps from the suspension to this space N. This is, again, space of maps. From the nth suspension to the nth space of this, space of this collection. And you basically look at the homotopy groups of this space. But of course, what you do, just like everything here is about stable phenomena. So you'll have to take the limit as n goes to infinity of this space of continuous maps equipped with this standard closed standard topology. And then these cohomology groups, they are just homotopy groups of these spaces. But what that means is that now I can tell you what it means for something to vanish at the chain level. Okay, for something to vanish at the chain level, it means not that some, whatever, there's some differential or something null homotopy. What it means is that this map of spaces is null homotopic. Okay, so this is again a familiar notion, nothing strange about it. The only thing that's a little bit strange is the fact that it's not just one space that you have to think about, is you have this kind of infinite collection of spaces. So really what it means is that there is some null, if you look at the finite part of your space X is finite. So this is not a problem. If X is finite, you can just say like there is n large enough so that things become null homotopic, and that's good enough. If X is an infinite space, then things become more tricky. Okay, so what that means is that we have to look, so when we say things vanish at the chain level, means finding null homotopies. But now, you could try to do it using machinery of stable homotopy theory, but in Floer theory, we have geometric objects, and we really are going to be studying kind of cobordism. And what I want to insist on is that these null homotopies, they don't come out of nowhere. These null homotopies, they come out of finding bounding manifolds. Okay, and the reason that you have to look at bounding manifolds is that the space for complex cobordism, this space N, this is basically the space of complex, stably almost complex, but let me just write it. Stably almost complex manifolds of dimension N. Okay. You have to formalize this notion. What do we mean by the space of almost complex manifold of dimension N? What it means is something like, this is a space whose zero simplices are such almost manifolds. One simplices are given by cobordisms between them. Two simplices are given by cobordisms, and so on and so forth. Okay, so but I want to insist is that this is a very geometric object, and if you are looking for a null homotopy in this space, what it means is a uniform way of finding null cobordisms. Okay, and Floer theory usually gives you plenty of such things. So that's somehow, that's how you should think about all this formal stuff. Okay, so now I can state the results. So this was proved, a paper was posted about a month ago now on the archive. The result is joint with McLean and Smith. And what we prove is this conjecture that I stated at the beginning, we prove it at the level of pi naught. Okay, so what this tells you basically is that the conjecture is that the parametric version of our result holds, and I'm very optimistic that we can prove it, but it's it would take a little bit more work. So the statement is, more precisely, if I consider a loop in the Hamiltonian diffeomorphism group. So in the previous notation, if you're trying to match up, this is just an element. So gamma from S1 to ham X is just an element, same thing as an element of what I called the base loop space of ham X. The first slide I said some map from the loop space, blah, blah, blah. So this is an element. So if you take such a map, then you can compose and obtain a map from S1 to the stable automorphism group, which means you obtain a map really from S1 cross X to X, okay? And similarly by suspension. And you could ask, what does this map do on homology? It induces a map from the homology of S1 cross X to the homology of X, okay? But this map, the homology of S1 cross X, I mean, Kunith doesn't always hold in generalized cohomology theories, but it will when you multiply by a circle. The most important thing we care about is that there is you look at the things which are, take the fundamental class of S1 times the class in X. So that's a map from the homology of X shifted by 1 to the homology of X. And this has a name. This is the sweep out map. Sweep out. Oops. So this map is, again, you take a cycle in X, you'll have a circle, the circle makes the cycle move around in one higher dimensional cycle, and you say, what do I get? Okay. And the statement is that this map vanishes with coefficients in any complex oriented cohomology theories. And I said spectrum level, but anyway, at the chain level, it vanishes at the chain level. And again, I'll come back in a second. So it vanishes on homology if you care about something very concrete. And well, that's the vanishing statement that we proved. This is pi naught, so statement on components for the conjecture. So this result was known earlier for rational cohomology. Okay, so Lalonde, McDuff, Polterovich have a paper which proves many other things, but it was basically some follow-up to the construction of the Seidel homomorphism. They proved it integrally in the monotone case. And if you look in their paper at the end, they say, you know, everything should work as long as there is the appropriate virtual fundamental cycle theory. And then McDuff later worked out this virtual fundamental cycle theory to actually work rationally for any closed symplectic manifold, so you don't have to assume monotonicity. Okay, so you know, now that we're working in this range where we aren't, so if, in particular we prove it integrally. But now we're working in this generalized cohomology context. You know, one of the first questions one should ask is, okay, we prove it for complex cobordism. What about other theories? What about stable homotopy? And it's very easy to come up with a counterexample, which is that if you just take the obvious rotation of, I'm going to use a different color just so that it stands out better. If you just take the obvious rotation of S2, okay, there's a circle that acts on S2 by rotations. That map is clearly trivial in ordinary homology. That's easy to see. There's just no, there's no, you know, the map vanishes for degree reasons. But if you look at real K-theory, so this is basically the K-theory of real vector bundle. Then this map is non-trivial. Okay, and so that's on the other hand, we prove that it's trivial for complex cobordism. So I don't want to suggest that the vanishing for complex cobordism is somehow completely optimal, like provably optimal, but this strongly suggests it, because somehow if you try to think about any natural geometric thing that's not complex cobordism, your first guesses are going to be basically like you know, oriented cobordism and real K-theory. And basically, oriented cobordism is constructed from complex cobordism and real K-theory. So once this is not true, I'm quite sure that this analogous thing is also false for oriented cobordism, but I haven't tried to prove it. So anyway, the statement, you know, it's not true that the map to the stable automorphism group of X is trivial, because that map is not null. You can detect it using real K-theory. And so it seems that the best we can do is this statement about complex oriented cohomology theories. Okay, so then I'm going to state a couple more results, and then pause for a second for questions. So this is construction that was known to you know, Lalonde, McDuff, and Polterovich. Once you have this result about loops in hand, you can conclude something about Hamiltonian fibrations, which is in the title. So the construction is as follows. If I give you a map S1 cross X to X, I can always associate to that, really what I should say, a family of diffeomorphisms parametrized by S1. I can always associate to that a fiber bundle over S2. And I'm going to call this phi here, and I'm going to call the fiber bundle P phi, and it projects to S2. And as fiber X, and you just construct it by taking the trivial product X cross D2 in the lower hemisphere and the trivial product X cross D2 in the upper hemisphere, and you just glue them along phi. Okay, at every point in the boundary circle, you use this value of the map phi of t. You attach the two things together. This gives rise to a Hamiltonian fibration, and vice versa. Okay. Every Hamiltonian fibration can be broken up like this, and that's just the statement that they are locally trivial. You look at a Hamiltonian fibration, you take over S2, you take the equator, you cut along the equator, you get two trivial pieces. Then, well, if you have these two trivial pieces, all you need is to glue back the fibration is this data of this family of Hamiltonian diffeomorphisms. So the corollary of the result, it takes a little bit of algebraic topology to prove, is that the Sayre spectral sequence for this fibration degenerates for every complex oriented cohomology theory, which in particular means that we have an isomorphism. Actually, the fact that we have an isomorphism is a little bit stronger than the degeneration of the spectral sequence, because there could be some filtration phenomenon. And in fact, we prove that this isomorphism, it again comes from the chain level. There is a our construction determines a map from the chains of P phi, which really means, again, some kind of space that is associated to some kind of space that is associated to the cohomology theory and to the total space of the fibration, and the associated space that is associated to X cross S2. So there is P phi, and there's X cross S2, and we just sent, they're not homotopy equivalents. There's no map between them. But if you pass to the chains of their cobordism theories, which roughly speaking, if you multiply them with these spaces En that I said kind of give you the correct notion of chains in the context of generalized cohomology theories, then they become equivalents. Okay? And this result has non-trivial content. The fact that you work on the chain level has non-trivial content, because it means, for example, that because we prove something for complex-oriented cohomology theories at the chain level, then when we reduce coefficients down to FP, so this is, I'm going to write Z mod PZ coefficients. I'm writing FP because I'm thinking about some multiplicative structure. Once we reduce coefficients, the isomorphism that we have of ordinary homology with FP coefficients, and this for this non-trivial fibration, the isomorphism between that and the one for the product respects some operations, respects some Steenrod operations. It doesn't respect all of them. For example, if you know something about Steenrod operations, the first one that you would think about after square one is square two. It does not respect square two. Okay, but it respects some elements called QI elements. They have degree approximately 2 to the I. I'm not going to try to get it right. So they're rather sparse. They're rather sparse in the Steenrod algebra, but nonetheless, there is a non-trivial subset of subalgebra of the Steenrod algebra, which is preserved by these operations. So we have kind of more content than you might guess by just stating the homology, stating the homology isomorphism. Okay, so I want to pause for a second and just ask for questions about the statements of the results, because the next part will be basically trying to give some indications of how this is proved. So, everybody happy? Okay, everybody happy. Okay, so what's the idea of the proof? So there's two parts.
Excuse me.
Yes, Leonid.
Yeah, I was just talking when I was mute. So you somehow said a while ago that you're looking only at linear structure, kind of, and in the corollary you have the separations.
Yes.
So how do you achieve this?
So it's just a feature of stable homotopy theory. So the point is, when I said if we take X and I look at this isomorphism from the homology of X to the homology with the shift of the suspension of X, it turns out that this isomorphism, it does not respect the cup product. However, it respects the Steenrod algebra operations. So this is known, it's known that the Steenrod algebras are stable. The Steenrod operations are stable. And so it's not like we prove anything fancy. It's just that, it's a consequence of the general theory.
Thank you.
Okay. So let's talk about the geometry of the proof. So this geometry that I'm going to describe is something that is, I don't know who really came up with it, but it's explained in McDuff's paper. So the idea is, remember, we have, there's several players. So I just want to remind you what's going on. So X is the fiber of this fibration over S2. Okay, so P, this P, which maybe we'll call it P phi, but let's call it P for now. This P has dimension 2 higher than X, because, well, 2 higher than X. Okay, so what we're going to do in this proof is that we're going to introduce a manifold whose dimension is even larger than that, like 1 higher than that of P. Okay, and that's going to be called P tilde. So how do we construct this? So the picture is here. Okay, so the key idea of the picture, this is like algebraic geometer's picture. Okay, this base here is the complex number. Okay, the fibers. Okay, there's going to be some general fibers, and they are drawn as straight lines. There's going to be one special fiber, which is this thing that's in the middle here. Okay, I don't know why I'm doing this, but anyway, this general fiber is going to be singular. I'm sorry, the special fiber is going to be singular. It's going to be fiber over 0. So this is a fiber over 0. It's singular, but it's not badly singular. it's just two smooth manifolds glued together along well, I was going to say along a divisor, but anyway, along a codimension 2 hypersurface. Okay, so what are these two smooth manifolds? It's just P of phi union along P of union with P phi inverse along X. Okay? So this loop of Hamiltonian diffeomorphisms, it determined this fibration. This is just the inverse loop. If you try to make a real, so it's difficult to draw in higher dimensions, but one picture you should have in mind if you don't like algebraic geometry pictures is that, you know, you could take with S2 and you can degenerate S2 to this, to two copies by like pinching the circle in the middle. And that constructs a total space, which is an algebraic surface. It lives over the plane, okay? So again, the key features that I'm going to use is that this total space, again, this thing that has dimensions 4 more than X, P tilde, it's a smooth symplectic manifold, okay? It's not a Lefschetz fibration. The singularities are not those of Lefschetz fibration. The singularities are more like the, you know, it's like it's the simplest type of normal crossing divisor, if you're familiar with the language of algebraic geometry. The smooth fiber, as I said before, and I say again, is a copy of X times S2. This is a smooth fiber. The singular fiber includes as a component one of the copies of the space that we care about. So roughly speaking, in the original proof, in the proof of the Seidel, in the construction of the Seidel homomorphism, what you do is you take holomorphic curves in this smooth fiber, which you know exist, and then you degenerate them to the fiber over 0. And you can use, you know, by Gromov compactness, you conclude that there must be some well, Gromov compactness and some little bit of regularity. You conclude that there must be some curves in the fiber over 0. Okay, so that's how Seidel constructed his homomorphism, and that's how Lalonde, McDuff, and Polterovich then used this kind of to conclude stuff about the Hamiltonian diffeomorphism group. But we don't quite have all those tools yet. We don't quite have quantum cohomology yet. Instead, we're just going to use this total space. Okay, so that's how we're going to use it. Well, it turns out that to prove, so we're going to focus on this consequence, which is this degeneration of the spectral sequence. Proving that this degenerates is actually the same thing as splitting the map from the homology of X to the homology of P. I'm going to put a phi. You need to split it. But it's easy to see that we can just compose one more time inside the homology of this object P tilde. And if we could split that, then we would be in good shape, because if you split the composite, then you split the original thing. Okay, so that's what we're going to focus on. We can kind of ignore the fact that we're working in the space P phi and this work in the space P tilde, which is bigger. Okay. So it's bigger, so it thinks that it makes you maybe worried about it. But in this space, there is a canonical class in pi 2, which is the class of these spheres. So this smooth fiber is S2 times X. So inside here you have S2 times a point. This is a canonical class of spheres that we can study. And you know, again, if you I'll say something at the end about, I'll repeat something at the end about the relationship with the earlier work. But for us, we just use this class. Okay? We look at the moduli space of genus 0 stable maps in this total space which have 2 marked points. This is kind of important, and which are in this class beta. Okay, and now there is some decoration here. There is this P tilde and C cross X, and what that means is that one of the marked points is basically free. It can go anywhere it wants. So it's decorated by P tilde, and the other marked point, I would constrain it to lie on C cross X. What is this C cross X? This is what we call the horizontal section, and I'll point it out in just a second. So the horizontal section, this is not the smooth fiber. It's the thing that kind of intersects it transversely. It's this one here. So remember, this fibration the reason this map to C, the reason it's non-trivial is because something happens where the two copies, where the two Hamiltonian fibrations are being glued together. Okay? But if you take a point that's away from that vibration, away from that gluing point, like imagine you're gluing at 0, and gluing the fibers over 0. So go to the fiber over infinity. So locally, nothing is happening. So you just have a section. So we look at the moduli space of holomorphic spheres, which pass through this section. So now we have this projection to C. So if you have this holomorphic sphere, and say it lives here, it kind of, it passes through a point that's far away from the singularity, then its projection is constant. It's constant projection. And once you realize that, and you also know its homology class, you understand that these spheres, again, away from the singular fiber, these spheres are just the obvious sections of S2 cross X that we have. And what we're going to use in a second is the Grove compactness tells us that the space of such compactifies to some closed, some compact topological space. Not quite compact because I made the base C, but anyway, to something which is proper over C. Okay? So let's not for a moment worry too much about the geometry of the space. All I want to say is that by definition, the space, which I'm going to summarize it, call it M bar 2, it has two evaluation maps, one to P tilde and one to C cross X. And I can use these evaluation maps to construct the map from the homology of P tilde to the homology of X. And let me explain how that map is constructed. First, we do step by step. First, we appeal to Poincaré duality. Oops, I guess that's okay. Poincaré duality, and we turn the homology of X into compactly supported cohomology. Then we pull back under evaluation. So everything so far is straightforward. But then the next step, there is some magic. The next step is the virtual fundamental cycle, or the virtual fundamental class. Once you're looking at the compactly supported cohomology of this moduli space, if you have a virtual fundamental cycle, you can cap against it and pass to homology, just like if you had ordinary homology. And then everything after that is trivial. So you now have an element of the homology of this moduli space. You can project to the homology of X cross C. This is just project, push, if you want to say, but I'm going to say project. And then you appeal to Poincaré, then you don't even put Poincaré duality. Then you say, oh, this is something in the homology of C cross X, but these are homotopy equivalents. This is the same thing as the homology of X. Okay, so everything is geometric. We just use Poincaré duality, as I said, which I told you we would use it, because that's why we assumed that, one of the reasons we assumed that E is complex oriented. And then there is this magical step where we use the virtual fundamental class, and I have to explain kind of why the virtual fundamental class exists. And again, the remark that I want to make here is that there's no appeal to the use of quantum cohomology, which means this gives a simplified proof. And if you only focus about this one conclusion of Lalonde, McDuff, Polterovich, you get this simplified proof, which doesn't use gluing. Now, what I mean by doesn't use gluing is that, what they did is they had to re-express. I'll explain what they did. They took this count of curves that take place in the smooth fiber, and they degenerated it to be some count of curves that take place in the singular fiber, which means some curves here and some other curves here. And then they had to kind of say, well, okay, we want to make sure that we can write down some algebraic expression for the results and express it entirely in terms of things living in one of the two components. And that takes some work. That takes some extra work. But here we don't use any of that extra work, and partly because we didn't have the tools. We don't yet have quantum cohomology, for this generality for us to use. Okay, any questions about this geometry?
Yes, there's a question in the chat actually.
Yes, I can try to find it. Takes me a second too. I got it. I have it. Okay. In which paper can we find the McDuff's reinterpretation? I think the paper is titled something about Hamiltonian fibrations. I'm sorry, I can maybe try to find it at the very end. Maybe somebody can say it on the top of their head, but sometime around 2001. Okay, So now it's clear that the main ingredient we need is this virtual fundamental cycle. Okay, and so let me remind you, we're doing generalized cohomology theories. So it would have been possible to do this using the same methods that I used with Andrew Blumberg in this other result about the Arnold conjecture. But on the other hand, that paper was hundreds of pages long, and it's not clear that we would have been able to write the current paper that I'm discussing as something of reasonable length using those methods. Okay, so instead we developed some ideas of McLean's and construct global charts in this context. So what do I mean by global charts? So I think the easiest thing is to just give you the definition, the statement of the theorem. So I'm looking at a closed symplectic manifold as before, and I fix a class beta, just like what we always do when we do some kind of Gromov theory. And for simplicity, and simplicity if we do this in higher genus, it really takes quite a bit more work, but we can do it, but we haven't done it. We haven't written it yet. We're going to look at genus zero curves. Okay, so we're going to look at the stable genus zero maps in X in a given class beta. And the claim is that this moduli space admits a global Kuranishi chart. And you can, I guess we're using the word Kuranishi for tradition's sake, because in some sense, all the complexities of Kuranishi theory are gone from this statement. So instead we have some slightly different complexities that arise. So what do we mean by that? It means, let me do things in a slightly different order. There is some almost complex, and we need almost complex, but for now you can ignore it. Almost complex manifold T. So this is what we call the thickening. Okay. This almost complex manifold has an action of a compact Lie group G. Okay. This action, and I keep forgetting to write it, I'm sorry, in these notes, this action has finite stabilizers. Okay. In addition, there is a complex vector bundle over T and a section. So the picture you have is there is T here, there is E here, G acts on both of them. This is the projection map. I'm not going to denote it by anything. And then there is this section S. And S is G equivariant. I should have written that it's G equivariant. Okay. And now this data is related to the moduli space that you care about as follows. If you look at S inverse of 0, which is the zero locus of this section, because S was G equivariant, this also has an action of G, and therefore you can take the quotient. And the statement is that the moduli space is homeomorphic, because I was careful not to, well, anyway, the moduli space is homeomorphic to this zero locus modulo G. So this is what I mean by global chart. If you know a little bit about kind of virtual fundamental chains, how they're constructed, what you would notice is that locally, this is what people normally talk about, except that they talk about the G being finite and they talk about the vector bundle being trivial. Normally people say, well, we have a small open subset of the moduli space. In that open subset, we can find a thickening, which is some manifold with a finite group action. And we can find usually trivial vector bundle, so a representation of G and a map from the thickening to G, so that the inverse image of 0 modulo the finite group is the little part of our moduli space. But we somehow, in this result, you just work globally. And the only real cost of working globally is that we have to introduce compact Lie groups. But the reality is that this compact Lie group is, as I write here, it's just a unitary group. Okay, and we prove that this is essentially unique up to the obvious notions. You can make T a little bit smaller, you can stabilize, you can enlarge group, all natural operations you can make in this context, and we find their geometric analogs. If we make some choices to construct this, and any two choices that we construct are related for this, are related by these moves. We also prove that this is smooth. This thickening is smooth, but our proof is not direct. So we don't use any analysis to prove this, or any, as we say, any hard analysis. Only things that are contained in McDuff Solomon's book. And well, to be completely honest, we also use things that are contained in the appendix to Pardon's virtual fundamental chain paper. only basically because he elaborates, kind of says things almost exactly in the context that we need them. But kind of fundamentally, there's not much going on beyond what's McDuff Solomon. But anyway, let me move on because I don't have that much time. Okay, so this is the main result. So this is the main technical result in some sense. Okay, that these charts exist. So so here in this slide, I kind of wanted to explain the construction. So the construction is kind of very, it's the starting point is very close to the one that Seidel and Monkey had, except again, we only do easy things. So they said, well, let's pick a line bundle and let's assume that the curvature is sufficiently close to omega to the class of the symplectic form. I don't remember whether in their paper they do this or they work with the integral symplectic form, but you could do this with, you could use their methods here as well. And now what we do is we can pull back. So we take this line bundle, we take a very large power of it, and we pull it back under the domain of to the domain of every map in the that represents an element of the moduli space. Okay, so now when we pick K to be large enough, the pullback of this line bundle is going to be a very ample line bundle on the underlying Riemann surface. And so therefore, we can look at the space of holomorphic sections. I mean, we can always look at the space of holomorphic sections, whether it's very ample or not. But the fact that it's very ample, the fact, on every single one of them tells us that the rank of the space of holomorphic sections is constant and doesn't depend on where we are in the moduli space. And this is, in some sense, the essential point. So then, by the ideas that underlie the construction of Kadira embedding, what you can associate to this data is so if you, in addition, choose a basis of the space of holomorphic sections, okay? You choose a basis of space of holomorphic sections, then you obtain a map to projective space, map from this fiber to projective space. So what that tells us is we introduce some notion, which is the notion of a framed map, which is exactly a stable map together with this unitary basis. The space of framed maps means that framed maps has a natural action of the unitary group. But more importantly for us, it makes a natural map to the, it gives you a map from the domain to complex projective space. So this moduli space of all such has a map to the moduli space of curves in projective space. And then the last property that we need is that when, this map to projective space, you can pull, it doesn't collapse any components. That's, the correct way to say this. It doesn't collapse any components. So what it means is that it stabilizes the domain. So in transversality, when you try to prove transversality for moduli space of holomorphic curves, always the problem is automorphisms. How to get rid of get rid of the automorphism problem. But here, this geometric data of the line bundle and the space of holomorphic sections and the pullback of the line bundle is sufficient to stabilize the problem. And everything is equivariant. So, with the action of this group, this group of unitary transformations, which basically just change the basis to another basis. So once you're here, if you know what you're doing, which means if you know how to construct, thickenings of moduli spaces, it's very easy. You can just choose data universally over the moduli space and obtain a thickening of not of the moduli space that you cared about itself, but of this unitary bundle, principal unitary bundle over it. So that's how I will say about the construction. I think if you have this idea and kind of, a little bit about pseudo-holomorphic curve theory, you can reconstruct a version of what we did. We were kind of more, we did something a little bit more complicated than strictly necessary because we were focused on finding this smooth, almost complex structure and so on and so forth. Okay, we wanted something kind of, slightly out of the obvious tools. If you just want to have a thickening and oriented one, and you're not worried about complex structures, you can just follow this outline and construct the desired thickening. Okay, I'm going to skip this slide. It's about smooth structures. Unless somebody really wants to ask about smooth structures, let's not worry about that. Okay, so now there is this magic point where I use the virtual fundamental class. So what does that mean? So remember, again, always the most important thing is Poincaré duality. So remember, we have this thickening, and it has this group action, and inside of it is this S inverse of 0. Okay. What we want to do is you want to use the thickening as a replacement for the moduli space itself. Okay. So instead of constructing a virtual fundamental class in the homology of the moduli space, I'm going to construct it in the homology of the thickening. But the thickening has this group action. So you want to construct it in the equivariant homology of the thickening. Okay? So we could try to imagine what would be a simple statement of Poincare duality for G manifolds. Okay? And it would be exactly, so the guess would be, well, okay, do you look at the G equivariant cohomology, and you look at the G equivariant homology, and they should be isomorphic up to shift. I mean, I didn't write the shift down. They should be isomorphic up to shift. And if you see there's some symbols, like here, there's the cohomology of T, and there's the cohomology of T rel boundary. That's because T is not closed. T does not need to be closed. I could also have done it with some kind of compactly supported things, but anyway. Now, let's assume that we have this Poincare duality statement. On the left-hand side, in cohomology is a ring. Okay? So in cohomology, there's always the unit element, 1. So you can look at its image, and its image is this fundamental class, the G equivariant fundamental class of T, of the moduli space, of the thickening. But now the thickening also has this vector bundle, and this vector bundle, again by Poincare duality, has an Euler class. This is the G equivariant Euler class of the vector bundle, and then you can just multiply them using the cap product. So we can define the fundamental class of the zero locus to be the image of the Euler class and the fundamental class under the cap product, and the cap product takes value here, takes value in the G equivariant homology of the thickening. So when I gave the sketch, I suggested that we wanted instead to have something in the homology of M bar, okay, and this homology of M bar is comparable to the G equivariant homology of S inverse of 0. But here I don't have it in the zero locus, I have it in the homology of the thickening. But it turns out that this is independent of the choice of thickening. If you take the thickening and you shrink it a little bit, then you have compatible system of virtual fundamental classes, and this is good enough for all applications. Okay. So for example, if you want to evaluate from M bar to like M bar, let's say 2 to X cross X, which is what we're going to do anyway, the image of, you don't need to produce the virtual fundamental class in the homology of M bar. You can just produce it in the homology of the thickening, as long as the thickening has an evaluation map. And this is obvious from our definition. Our thickening obviously extends to a space with a map to X. So therefore, you can push this map, this fundamental class, under your evaluation maps. Okay, I'm slightly running out of time. So, but what I want to say is that the previous slide, okay, suggested that we should look for Poincare duality of this form. Okay, the G equivariant cohomology and homology are isomorphic. However, this is very rarely the case. Okay, and the reason is because when you take G equivariant homology, you're taking homology in the direction of, in some sense, in the direction of the manifold and in the direction of G. Okay, and we take cohomology, the same thing happens. You take cohomology in the direction of manifold, but also in the direction of G. And that's kind of, makes it very unlikely to expect that you have such an isomorphism. And as I write, if you want to have an isomorphism with like, FP cohomology, for example, this only works if the cardinality of the isotropy groups is relatively prime to the characteristic. Okay, so this, again, the key, this almost never holds in this form. And this is why the paper is, this is why we have some additional complexity. We cannot directly work with, let's say, we could actually work with G-equivariant borders, but anyway, we cannot work with ordinary homology theories. How about that? Directly, like complex cobordism or integral homology, we can't do that directly. Instead, we have to work with kind of these exotic cohomology theories, which are called the Morava K-theories, which are in some sense the only ordinary cohomology theories for which this isomorphism holds universally, without any assumption on the geometry of T. Okay. This is a theorem from about 10 years ago. proved by a stable homotopy theorist. And it basically says that there are cohomology theories called KN for which this isomorphism holds. Okay, so it builds on a long string of computations in the subject. But we use it, and I just want to say again, this is a result that Andrew Blumberg and I used earlier in the Morava paper. So unfortunately, I don't have much time to talk about KN local theories. I will just end with this picture. So this picture is as follows. So here there is ordinary arithmetic, so usual arithmetic, and in the usual arithmetic we have abelian groups, but literally say we have the integers, and we look at all the primes for the integers, and each one of them is the familiar primes, prime numbers. So you can localize the theory of abelian groups at a given prime, and well, not exactly, but then what you get is the theory of working in characteristic P. So you can work in characteristic 2 or 3 or P or whatever you want. And there's one other prime at infinity in some sense, which is working rationally. But in this picture, it shows up in a different way. Now, in some sense, what there is a bigger picture where you can call it maybe like higher arithmetic. And that is related to the sphere spectrum. And in higher arithmetic, you still have the usual primes, but each of the usual primes has some kind of other, it kind of decomposes into finer primes. And these finer primes, they are labeled by natural numbers called the height. This is a natural number. And there is one additional prime for each of these natural numbers, and those are called the Morava K-theories. So this picture suggests that the way you want to prove things, if you cannot prove things directly, one way to prove things is to take your result, decompose it one prime at a time, prove the result for the given prime, and then try to reassemble. Okay? And that is exactly what we do. We essentially prove things for each Morava K-theory, and then use, just like in usual arithmetic, if you have a result that holds for all primes, you can say, oh, well, therefore, because of some maps gluing things together, I can conclude that it holds at the level of abelian groups. So you can do the same thing here. And that's the last part of our strategy. So anyway, sorry for running over, and thank you for your attention.
Thank you very much. Okay, so are there any questions? Maybe I can start with a very simple one. I just naively wonder if there is some cases where this allows to completely understand the pi case of Ham or
I don't know, but the thing is, I don't know very much about the kernel, right? I mean, somehow, I mean, even this first one, I just don't know what to. I mean, we have some results. I think actually I have not thought about the literature. I know that if you think of Ham as the connected component of the identity in Simp, then we know a lot about, we know that the kernel from Ham to Simp generically, well, not generically, can be very large. I also know that we don't understand it in any example above dimension 4. So the higher homotopy groups of Ham, I actually haven't thought about in that. My guess is that that's die under this map. I haven't thought about it, and I don't. There's probably people in this audience that have thought about it. Maybe they can say something. So anyway, so from my perspective, that's why I can't say much.
So when you say the kernel in this context,
I meant just already this.
Okay.
That's what I meant. I mean,
so
of course,
that even for Simp in this case, it's not clear.
Well, all I'm trying to say is that if you look at pi 0, no, so I was first thinking about pi 0 simp to pi 0 diff. So this, we have, plenty of examples of things in the kernel, for example, Dane twists. But yeah, so it's in the kernel.
Okay.
But for Ham, I don't know what to say because I haven't thought about trying to construct families of elements of Ham that are smoothly trivial, but not symplectically trivial. I suspect that there is a literature, but I haven't tried to understand it.
Any other question? This Morava K-theory, I mean, to me, it's totally mysterious.
Yes.
Why was it developed originally, or?
It was. I mean, I think the short answer was developed for this picture. But I think another thing, it was developed for. Okay. So it was developed for this picture, but somehow it was studied a lot in the 1980s because it was hoped that this picture would allow one to understand the stable homotopy groups of spheres. So the idea is supposed to be, you're interested in the stable homotopy groups of spheres. Very early on, like already with Serre's thesis, we know some interesting results about the stable homotopy groups of spheres P localized. So if you like the stable homotopy groups of spheres completed at the prime P vanish in some range which is linear in P. Okay? So if you're less than or equal to some constant times P, so pi K stable of, well, anyway, of the sphere, this is equal to 0 if K is less than or equal to some constant times P, which I could always remember is equal to 0 if K is less than or equal to some constant times. So already was known that, if you have some kind of arithmetic tools, you can start proving some non-trivial results. Okay, so now the hope would be that you would do something analogous with these groups. You would then try to use them to compute the Kn localization. So that's the name for this, for the homotopy groups that are detected by this specific prime, and then you would try to reassemble together. But this strategy kind of was a complete failure in the sense that somehow the only thing they managed to do is the thing that they already had before, which is compute this first layer. And this first layer at the very bottom is basically related to ordinary K-theory. And the second layer, there's just you can't do anything. And the reason is kind of interesting. The reason is that they don't have geometric models. So that's what prevents progress. But for us, we don't, we're not, I mean, again, these applications, they don't require any subtle computation of some, homotopy group in some range. They're kind of, it's all about structure. And the structure, they're very good. The algebraic topologists are very good at building structure. So it turns out that they more or less build exactly the structure that we needed.
Okay, thank you. More questions or comments?
Maybe a remark that in complex geometry,
yes,
this story was considered, I think, in '56. So, real cohomology of fibrations over S2. So
okay.
It was a work of Blanchard, but he somehow used complex methods, and so which were, of course, quite different from what we use. But now you are using, you have another proof. So maybe it would be interesting to compare with the original argument of Blanchard.
Actually, that's very interesting. So the only reference that I knew is that, so Pierre Deline proved that if you take any smooth, so I'm going to take P over B. So if you take any map of smooth projective varieties that is non-singular, So this is smooth map of projective varieties. So the lean developments of Hodge theory implies that the Sayre spectral sequence degenerates rationally. So I was not aware of the earlier literature. What's interesting is, I just want to say this is not true integrally. And it's also, this is related to the question that there's a conjecture at the beginning where I was asked, like, do I make a statement about Ham X, mapping to this automorphisms? I'm not making a statement because there is a counterexample, and the counterexample is already on S2, which is that, if you take the universal fibration, I'm going to say it like this: if you take the universal fibration over BSO3 with fiber S2, let me just call it BSO3. So SO3 clearly maps to Ham of S2. So this spectral sequence does not degenerate integrally. It doesn't degenerate with Z-mod 2 coefficients. And the reason it doesn't degenerate is because of the presence of the elements W3 in the cohomology of BSO3. So this is basically the witness to the non-vanishing of this spectral sequence. So now this is not, however, this element dies upon taking loops. If you pass through the loop space and you look at the associated maps, then it's not a problem. So this is something I find this actually very interesting, because it suggests that, like, our basic things from algebraic topology already tell us that some constraints as to how much we can expect to push this vanishing.
There's a question in the chat also by, there's a comment by Ivan, which is related to my question. And there's also a question by Zengi Zhu.
Can the global charts? Yeah, so so the question is, I'll read it. Can the global charts be used to prove the equivalence between symplectic and algebraic Gromov-Witten theory? It's very tempting. So right now we're at the stage where our global, in fact, part of the reason that our construction of global charts is not the simplest possible is that, in fact, the total space of our global chart is a complex variety. And the vector bundle on it is a holomorphic vector bundle. Okay, the section that we use is not holomorphic. Okay, so there's some interesting question as to, is there some way of slightly twisting our construction to get something which is a holomorphic section, in which case then we would basically be done. But yes, it's somehow it's very appealing to think that we're very close. I feel like we're very close to proving it, but there are many other things to do as well. And I think again, currently what we're trying to do first is just write up the higher genus version, and have a robust theory. But just to say one thing, like, I think the thing that this is most adapted for is the following setup, which is take your X and assume that it has a Hamiltonian group action by some other group H. Then it immediately follows from our construction that we have a global Kuranishi chart, which not only has this action of this unitary group, which is which is the thing that you kill, but actually also has an action by this H. So everything is equivariant. So if you wanted to study, how does Gromov-Witten theory interact with group actions, it's made for this. Yeah, so localization is almost free. Yes, somehow you have to formulate it, but yes, yes. Sorry, Jengi continues to write in the chat that yes, it looks like localization is just a consequence of the classical localization for G actions on manifolds. But again, we haven't written it, and it would be good to write it just for rational Gromov-Witten theory, which is what people use localization for. The most. It's hard to use localization in higher generalized cohomology theories. Yeah, and this is why the talk is organized like this.
Okay, so I guess we can thank Mohammed again for this wonderful talk.
Thank you.